Usually when we talk about human progress, we picture this, like relentless, victorious march of knowledge.
Right, like we're always moving forward.
Yeah, exactly. We like to think of science as someone slowly filling in a giant cosmic crossword puzzle. Every discovery is just, another word locked in.
It's a comforting thought, honestly.
It is. But if you look closely at the history of human understanding, a completely different and, frankly, much more humbling picture emerges.
Oh, absolutely.
It turns out ignorance isn't a shrinking puddle. Ignorance is actually a lot like the expanding universe. Every time we accumulate a new piece of knowledge, we don't just fill a gap. We stretch the boundaries of reality.
We unveil entirely new, massive pockets of the unknown that we didn't even realize were there.
Exactly. And that brings us to the mission for our deep dive today. We are pulling from this fascinating book by George G. Szpiro called Ignorance, What We Do Not Know, Cannot Know, Must Not Know, and Refuse to Know.
Such a great read. And our goal today is simple, really. We want to completely redefine your relationship with the unknown for you, the listener.
Because how we view that unknown actually depends a lot on our cultural starting point. Szpiro points out this really interesting divide early in the book.
Right, the cultural differences.
Yeah, he brings up that famous 17th century carving of the three wise monkeys at the Tushkuju shrine in Japan. The one see no evil, hear no evil, speak no evil.
Everyone knows that image.
Right, but Szpiro notes that in traditional Eastern and Confucian thought, this kind of intentional ignorance like turning a blind eye is often viewed as a noble propriety. It's virtuous.
Which is so different from how we see it in the West.
Completely. He contrasts that with the Western perspective, where feigning ignorance is usually viewed as, spinelessness.
Or just flat out complicity.
Exactly. In the West, looking the other way feels like the mafia's code of omerta. It's a bad thing.
It is a profound cultural observation. But for this deep dive, Szpiro asks us to kind of set aside those moral judgments and focus instead on the pure mechanics of the unknown.
Okay, so where do we start?
We're going to tackle two of his major categories to help you navigate this expanding universe of the mind. First, we will look at the things we simply do not know yet.
The do not knows. Got it.
Right. And then we're going to look at a much more intimidating category. The things that the fundamental laws of reality dictate we literally cannot know.
Man, I am so ready for this. Let's start with those do not knows, because we don't even have to leave planet Earth to find a massive one.
You're talking about the ocean.
I am. I'm talking about the deep sea.
Ah.
It is quite literally aqua incognita. Back in 1960, the explorer Jacques Piccard and U.S. Navy Lieutenant Don Walsh did something incredible.
The Challenger deep dive?
Yes. They climbed into a bathyscaphe to dive to the very bottom of the Marianas Trench.
And just to put that dive in perspective, they were descending nearly 11 kilometers below the surface of the ocean.
Which is just, it's hard to even fathom.
It is. The pressure down there is roughly 1,000 times the atmospheric pressure you and I feel at sea level. It is the equivalent of having dozens of jumbo jets just stacked on top of you.
Oh, wow.
Yeah, so to survive that, they had to be encased in a spherical gondola. The steel walls were 12 centimeters thick.
And they actually made it. But the crazy part is what they reported seeing when they finally hit the ocean floor.
The fish.
The fish. They claimed they saw a flat fish, something resembling a flounder, just casually swimming away from their floodlights.
Right, and why does that matter so much today?
Because modern unmanned probes with high-tech 4K cameras have gone down there since. And they haven't found a single fish at those depths.
Not one.
Not one. Biologically speaking, fish just shouldn't be able to survive that pressure. Their cells should basically collapse.
Right, the biology doesn't make sense.
Exactly. So that 1960 sighting remains totally unverified. We literally know more about the surface of the moon than we do about the biological reality of our own ocean floor.
And the mystery only scales up when we look outward. If we leave the ocean floor and, look up at the cosmos, the gaps in our knowledge become mathematically staggering.
Okay, let's go to space.
So in the 1930s, an astronomer named Fritz Zwicky was observing the Coma cluster of galaxies. And then decades later, Vera Rubin was studying the Andromeda galaxy.
Right.
They were both looking at planetary and galactic motion. They were specifically trying to apply Kepler's third law to the universe.
Okay, wait, let me give a quick refresher on Kepler's law for everyone. It's basically what governs how things orbit.
Exactly.
So think about our solar system. Mercury is super close to the sun, so it orbits incredibly fast. Neptune is way out on the edge, so it orbits much slower.
The further you get from the center of gravity, the slower the orbit should be. That is the fundamental rule.
Right, but when Vera Rubin looked at Andromeda, the rule seemed to just break.
It fell apart completely.
She discovered that the stars in the outer edges of the galaxy were moving way too fast.
Which is a huge problem, because when astrophysicists calculated the visible mass of the galaxy, all the stars, dust, and planets we can actually see, there simply was not enough gravity to hold it all together at those speeds.
Imagine a spinning merry-go-round. If it spins too fast, the kids are going to fly off unless they're holding on really tight.
Perfect analogy.
Galaxies are spinning so fast they should literally be flying apart into deep space. The holding on force of gravity just wasn't strong enough.
So to explain why the galaxy wasn't flying apart, scientists realized there had to be some invisible mass providing extra gravity. Dark matter.
Right, dark matter. It's a lot like the wind. You can't see the wind, but you know it's there because it moves the trees.
In this case, we can't see dark matter, but we know it must be there because its gravity is steering entire galaxies.
But, okay, I have to push back on this because this has always bothered me.
Go for it.
If we are saying that 85% of all the matter in the universe is totally invisible and completely undetectable to any instrument we have, how do we know our math isn't just fundamentally broken?
That is a very common question.
Like, why assume invisible matter instead of just admitting we don't really understand gravity?
It is a totally valid skepticism. But astrophysicists don't just guess right. They use a mathematical principle called the virial theorem to check their work.
Okay, what does that do?
Well, without getting bogged down in the equations, the virial theorem essentially balances the kinetic energy of a system.
The energy of motion.
Exactly. It balances that against its gravitational potential energy. Think of a roller coaster. The energy it takes to climb the hill is perfectly balanced by the energy of the drop.
Okay, I follow that.
When scientists apply this theorem to galaxies, the math holds up perfectly, but only if you factor in a massive amount of unseen matter.
Wow.
Yeah, gravity simply does not work the way we observe it working across the universe without this hidden mass. We are left profoundly ignorant of what 85% of physical reality actually is made of.
That is just wild to think about. And it gets even more disorienting when we try to figure out the fate of the entire universe, right?
Oh, absolutely.
We know Georges Lemaitre gave us the Big Bang Theory, but now we're wrestling with dark energy, which is this mysterious force pushing the universe apart.
Right, it's a cosmic tug of war. Gravity is pulling things together and dark energy is pushing them apart.
And depending on which force wins, there are a few ways this whole universe experiment ends.
It all hinges on a single vital metric called critical density. Scientists calculate that for the universe to perfectly balance expansion and gravity, there needs to be about 5 to 6 hydrogen atoms per cubic meter of space.
Just 5 or 6 atoms, that's nothing.
It's tiny. But if the actual density of the universe is greater than that, gravity eventually wins the tug-of-war.
Okay, what happens then?
The universe stops expanding, it reverses, and we get the big crunch. Everything collapses back into a singularity. Or perhaps a big bounce where it crunches and bangs all over again.
But what if the density is lower than those 5 atoms per cubic meter? Then dark energy wins.
Yes. The expansion accelerates completely out of control. Eventually, the space between galaxies expands so fast they disappear from view. Then the space between stars expands.
Oh, man.
And finally, dark energy literally tears molecules and atoms apart. That is known as the Big Rip.
The Big Rip. That sounds terrifying. And what if it sits right exactly on the edge of that critical density?
Then the universe just expands, slowing down but never quite stopping, cooling off forever. That results in the Big Chill. Total darkness, zero thermodynamic activity, just cold, dead space.
Okay, so we have the crunch, the bounce, the rip, and the chill.
Right. And the punchline here, because we cannot accurately measure dark matter and dark energy, we simply do not know which scenario is our actual destiny.
So our senses completely fail us when we look out at the vastness of the cosmos, and they fail us when we look down at our own ocean floor.
They really do.
But, we usually take comfort in assuming that at least our internal reality, our own mind, is reliable.
That's the assumption, yeah.
Yet if we dive into Spiro's research, the data shows our internal blind spots might actually be our biggest vulnerability.
Human cognition is perhaps our most intimate area of ignorance. A perfect and somewhat hilarious example of this is the Dunning-Kruger effect.
Oh, I love this one.
It was identified in a famous 1999 Cornell study by psychologists David Dunning and Justin Kruger. They wanted to understand a very specific metacognitive skill.
Like, how well can people accurately evaluate their own competence?
Exactly.
And the setup for this study is legendary. They tested people on three things: logical reasoning, grammar, and funniness.
Funniness is such a weird metric to test.
I know. For the funniness test, they literally had participants rate the humor of 30 different jokes, and then they compared those ratings against what professional comedians thought.
Right. And the math of the results is just staggering.
It really is. People who scored in the bottom 12th percentile, meaning they did worse than 88% of everyone else taking the test, genuinely believed with total confidence that they were performing in the 68th percentile.
Which introduces a devastating psychological track. It is the catch-22 of incompetence.
How so?
Well, think about the grammar test. To recognize that you are bad at grammar, you need a solid understanding of the rules of grammar.
If you don't know the proper way to use a past participle, how could you possibly know you just used one incorrectly?
Exactly. Therefore, unskilled people are literally too unskilled to know they are unskilled. They lack the exact metacognitive tools required to diagnose their own ignorance.
I mean, just think about the last time you saw someone arguing in a comment section online about a highly complex topic they clearly just Googled 5 minutes ago.
We've all seen it. We've all probably done it.
Totally. That is the catch-22 of incompetence in action. If you can't see your own incompetence, you can't recognize true competence in experts either, which traps you in a bubble.
It's a huge blind spot. But as deep as that psychological blind spot is, it doesn't even touch what philosophers call the hard problem of consciousness.
Okay, yeah. Let's talk about consciousness.
This takes our internal ignorance to a structural level. When we study the brain, researchers separate the challenge into two parts. First, there is the easy problem.
Which involves mapping the physical mechanisms, right?
Right. We can put you in an fMRI machine and see exactly which neurons fire when your eyes process the color red or when your brain retrieves a childhood memory.
So it's an incredibly complex biochemical and engineering puzzle, but it is scientifically solvable.
Yes.
So the easy problem is like understanding the hardware. It's mapping the wires, the pixels, and the circuit boards inside a television set.
Great analogy.
But the hard problem is trying to explain why the movie playing on that TV makes you cry.
Yeah.
It's the subjective internal feeling.
Exactly. The feeling of being alive.
But honestly, I have to ask, isn't calling it the hard problem just a bit of a philosophical cop-out?
What do you mean?
Well, aren't we really just waiting for our brain scanners to get high def enough to eventually map the feeling of a memory? Like, won't technology solve it?
That is exactly what a lot of scientists assumed. In fact, this debate culminated in a famous 25-year wager.
Oh, I've heard about that.
Yeah, in 1998, the neurophysiologist Christoph Koch made a bet with the philosopher David Chalmers. Koch bet a case of fine wine that within 25 years, science would identify the exact neural patterns that explain consciousness.
The physical signature of feeling.
Right.
Okay, so 1998 to 2023, we've had massive leaps in neuroscience since then.
We have. We've developed incredibly advanced frameworks like integrated information theory, or IIT, which attempts to mathematically quantify how information is unified across different regions of the brain.
Right, so who won the bet?
When 2023 rolled around, Koch had to publicly concede and buy Chalmers the wine.
Wow, he lost.
He did. Even with all our new scanners and math, science still cannot bridge the gap. We can measure all the objective third-person data of a brain lighting up. We remain fundamentally ignorant of how those objective biochemical sparks generate a subjective first-person experience.
We have literally no idea how the physics of the brain manufactures a feeling.
None.
Okay, so if our subjective minds are this murky, and we can't even trust our own perception of our own skills, we usually retreat to the cold, hard, objective world of mathematics.
Right. Math is a safe harbor. Or so we think.
Yeah, math has undeniable proofs. But here's the part of Szpiro's book that I found genuinely terrifying. Even our most advanced mathematics is built on top of massive pockets of profound ignorance.
The bedrock of modern math is remarkably fragile. Consider the Riemann hypothesis, which is arguably the most famous unsolved problem in mathematics.
Okay, tell us about Riemann.
In 1859, the German mathematician Bernhard Riemann made a brilliant hunch about a complex mathematical function called the zeta function.
And to translate the math into something we can visualize, think of prime numbers of just like 2, 3, 5, 7, 11.
The atomic building blocks of all other numbers.
Exactly. But they seem to appear completely randomly on the number line. Riemann was looking for a hidden pattern, like a secret rhythm to how prime numbers are distributed.
Yes. He proposed that the distribution of primes is deeply connected to the zeros of this zeta function.
Zeros.
Yeah, you can think of these zeros like the specific frequencies on a musical tuning fork. Raymond guessed that all the important or non-trivial zeros would line up perfectly on a single vertical line on a graph known as the critical line of 1/2.
And mathematicians have been obsessing over this tuning fork ever since.
Obsessing is the right word.
Recently, we've used crowdsourced supercomputers to check 10 trillion of these zeros. 10 trillion.
That's a lot of computing power.
And every single one of them lands exactly on that 1/2 line. So logically, it seems true. But here's the catch. In mathematics, 10 trillion examples do not equal the definitive proof.
Nope. All it takes is one single zero out of place, hiding somewhere out near infinity, to blow the whole thing up.
And if that happens, it brings down a mathematical house of cards, doesn't it?
It absolutely does. Because mathematicians are impatient, there are currently hundreds of modern mathematical theorems that literally begin with the foundational assumption, assuming the Raman hypothesis is true.
Wow.
Yeah. If someone proves it false tomorrow, all of that resulting mathematics instantly collapses. The foundation washes away.
And if you're listening and thinking, okay, but how does abstract math affect my daily life?
Right.
Well, it brings us to another massive mathematical mystery with massive real-world stakes.
P versus NP.
Yes, this is an unsolved problem all about computational time.
Right. P stands for polynomial time. That essentially means a computer can solve the problem manageably fast.
Okay.
And NP stands for non-deterministic polynomial time.
Which is just a fancy way of saying exponential time.
Exactly. That means the problem gets so complex so fast that it's completely unmanageable for a computer to solve from scratch.
Do we have a tangible example of this?
A great example involves prime numbers, again, specifically semi-primes. If I ask a standard computer to multiply two massive prime numbers together, it can do that instantly.
Because that is a P problem. Fast and easy.
Right. But if I give the computer that massive resulting number, say a number that is 500 digits long, and ask it to reverse engineer it to find the two original prime factors,
That would take forever.
it would take a supercomputer longer than the lifespan of the universe. It is an NP problem.
Okay, let me try to put this in a daily analogy.
Hmm.
PVS-NP is basically like a padlock.
Okay, I like that.
Finding the one right key in a pile of a billion keys is incredibly hard and takes forever. That's exponential time. But taking a specific key and checking if it fits the lock, that's instant.
That's polynomial time. Checking the answer is easy, finding the answer is nearly impossible.
There is actually a $1 million prize from the Clay Mathematics Institute for anyone who can definitively prove whether P equals NP.
Which sounds like a fun puzzle until you realize the implications.
Right, because wait, if I take that padlock analogy further, all of our internet cryptography, your banking passwords, secure messages, everything relies on these hard functions.
It does.
It relies on the assumption that reversing the math is practically impossible. So aren't we just crossing our fingers and hoping nobody cures this specific piece of ignorance?
You've hit on the terrifying reality of our digital age. Our entire global security infrastructure functions specifically because of our mathematical ignorance.
That's crazy.
We rely on the fact that no computer has the lifespan to check every single prime number key. If someone proves that P equals NP, meaning they discover a mathematical shortcut that turns these impossible exponential problems into fast polynomial ones, modern encryption is rendered completely useless overnight.
We are heavily financially invested in keeping that unknown.
Very much so.
Okay, that is deeply unsettling. But, saying we might figure it out one day or actively hoping we don't still implies that the answer is at least out there waiting to be found.
True.
Let's look at Szpiro's final category. Because it's one thing to say we haven't solved it yet. It's another thing entirely when the universe puts up a brick wall and says, you are physically barred from ever knowing this.
We are crossing the boundary from the do not knows into the cannot knows.
It cannot know.
This shifts our perspective from a temporary lack of information to hard limits imposed by the laws of logic and physics. A perfect historical framing for this shift is the ignorabimus controversy.
When was this?
In 1872, a German physiologist named Émile Dubois-Reymond gave a highly controversial speech where he declared ignoramus et ignorabimus.
Which translates to what?
It means we do not know and we will never know certain fundamental truths about the universe.
Which, predictably, made a lot of ambitious scientists extremely angry.
Oh, they hated it, especially the great mathematician David Hilbert.
Right. In a 1930 radio address, Hilbert aggressively pushed back against this defeatism. He famously declared, "We must know, we shall know."
Hilbert was an absolute optimist about human potential, but the universe had a different plan.
Yeah, it did.
Shortly after that broadcast, the brilliant logician Kurt Gödel dropped the hammer with his incompleteness theorem.
Gödel proved, mathematically, that Hilbert was entirely wrong.
Completely wrong. He demonstrated that within any consistent, formal logical system, like basic arithmetic, there are true statements that can never be proven using the rules of that system.
It's like being locked inside a windowless box and realizing you need a tool from outside the box to prove the box actually exists. You are forever trapped by the rules of the system you were in.
Exactly. And it's not just abstract logic either. We see these hard limits in physical geometry, too. Think about Benoit Mandelbrot's famous 1967 paper, How Long is the Coast of Britain?
It sounds like a simple geography trivia question.
It does, but Mandelbrot used it to expose the bizarre reality of fractal dimensions.
How does that work?
Well, if you try to measure the coast of Britain using a map that has a scale of 400 kilometers to a single centimeter, you get a specific length.
Right.
But if you use a much more detailed map where a centimeter equals only 100 kilometers, the total length actually increases.
Because you are suddenly capturing more of the tiny jagged inlets and bays that the bigger map just smoothed over.
Exactly.
And if you physically go down to the beach with a standard foot-long ruler, the coast gets unimaginably long because now you're measuring the perimeter of every single pebble and boulder on the shoreline.
Because the coast is self-similar, meaning the jaggedness looks just as chaotic no matter how close you zoom in, it actually has no true definitive length.
It mathematically cannot be measured.
Right. It only has a fractal dimension, which for Britain is roughly 1.2.
It proves that nature actively resists our attempts to perfectly quantify it.
Yes, and this inherent resistance is the entire foundation of chaos theory.
Which brings us to Edward Lorenz, right?
Yes, the meteorologist. He discovered this limit entirely by accident in the 1960s when he was running computer weather simulations.
He wanted to re-examine a sequence, and to save processing time, he started the simulation from the middle.
But instead of entering the exact data point of 0.506127, he truncated the decimals and just typed in 0.506.
Just a microscopic rounding choice, like
Yeah.
a fraction of a difference.
But that minuscule truncation led to wildly, completely different weather patterns by the end of the simulation.
And this became known as the butterfly effect.
The idea that a butterfly flapping its wings in Brazil could set off a tornado in Texas, because the weather is a complex nonlinear system, the tiniest immeasurable change at the starting line creates massive chaos down the road.
Since it is physically impossible for us to measure every single atom of the Earth's atmosphere down to the infinite decimal point, perfect weather prediction is officially a cannot know.
Exactly. Which brings us to the ultimate hard limit, the absolute bedrock of physics, Werner Heisenberg's uncertainty principle.
Oh, this is fascinating. There's a great joke in Spiro's book about a physicist named Dr. Makanos who gets pulled over for speeding.
I love this joke.
He asks the cop, "Where exactly was I and how fast was I going?" The cop checks his radar and says, "You were exactly 7.5 kilometers past the intersection, doing exactly 115 kilometers an hour."
And what does Dr. Meccano say?
He turns to the judge and says, "Your Honor, according to Heisenberg's uncertainty principle, you cannot know an object's precise position and velocity at the same time. The cop is mathematically lying." And the judge dismisses the ticket.
It is a wonderful, absurd illustration of a very real quantum concept. Think of it like trying to take a photograph of a speeding bullet.
Okay.
To get a perfectly sharp image of exactly where the bullet is, its position, you need an incredibly fast shutter speed.
Right, freezing it in time.
But in that frozen photo, you have no visual data on how fast it's moving its velocity. Conversely, if you leave the shutter open to capture its motion, you get a blur.
You know its path and speed, but you no longer know its exact pinpoint location.
Right. In quantum mechanics, to see an electron, you literally have to bounce a photon of light off of it.
Yeah.
But the physical impact of that photon instantly changes the electron speed.
So the sharper your measurement of one trait becomes, the fuzzier the other must physically be.
Exactly.
Okay, I love the camera shutter analogy, but I have to push back on the math of the joke for the real world. Go on.
If you actually run Heisenberg's formula for a macroscopic object, like a 2,000 kilogram car on the highway, the error in velocity calculation comes out to something like 10 to the negative 40 kilometers per hour.
Very, very small.
That is an unimaginably small fraction of a millimeter. Doesn't that prove Heisenberg's principle is just neat quantum trivia that has zero actual effect on our daily lives?
You are absolutely right about the math. The judge in the joke was scientifically wrong to dismiss the ticket because for a massive object like a car, the quantum uncertainty is entirely negligible.
Right.
But the reason this principle matters so much to Spiro's thesis is the profound philosophical point it establishes about the universe itself.
The ultimate limit.
Yes, at the very bedrock of reality, nature demands a tax of ignorance. It physically forbids us from having a perfectly clear, perfectly simultaneous picture of reality.
It's not a failure of human engineering or a lack of better tools?
No, it is an undeniable law of nature.
Man. So where does this leave us? We have gone on an incredible journey today.
We really have. We started at the pitch-black, unmapped floor of the deep ocean, zoomed out to the invisible limits of our expanding universe, traveled inward to the blinding blind spots of our own consciousness, and finally slammed into the hard mathematical walls of reality itself.
It's a lot to take in. But if we bring this all back to you, the listener, realizing the vast scale of our ignorance is actually incredibly empowering.
Empowering.
Yes, because you are someone who clearly loves to learn. Understanding the crucial difference between what we don't know, which should be the ultimate fuel for your endless curiosity, and what we cannot know, which should teach you peace, acceptance, and humility.
That is the ultimate intellectual life hack.
It really is. It shifts your whole relationship with information from anxiety to exploration.
Which brings us to a final, provocative thought from Spiro's book to leave you with today. It involves Meno's paradox.
Yeah.
In an ancient debate, a general named Meno challenged Socrates with a brilliant logical trap. He asked, "If you are completely ignorant about a subject and you don't know the answer to something, how would you even know you found the right answer if it hit you over the head?"
It is a devastating puzzle. If you are entirely ignorant, you lack the context required to recognize the truth.
Exactly. So next time you find yourself frantically scrolling, searching for an answer online, or wrestling with a massive life decision, stop and ask yourself something.
Do you actually know enough about what you are looking for to recognize the truth when you finally see it?
Or are you just wandering around in your own expanding universe of ignorance? Keep exploring that universe.